All right, Gordon is first up. Gordon's going to take us through drill site plug and play and reusable control systems. Gordon works at Xodus Group. He's a senior consultant. I think the best thing you need to know about Gordon is he's got a mate that works for Diageo, quite a head honcho. So if you ever need a really good bottle of whiskey, this is a really handy man to know. Over to you, Gordon.
Good morning. The first study awarded to Xodus was to look at the plug-and-play approach to small pool drill sites. So, what is plug-and-play? The OGTC's definition is interconnectivity, connecting modular equipment easily and effectively to form a production system that is fit for purpose and rapid to deploy. So the objectives of plug and play is to provide a quick delivery to site, connectivity between a range of modular components, and to reuse components multiple times from field to field, and to make use of a wide range of suppliers for the equipment needed. So as a result of our work, the picture on the right-hand side is our vision of the plug and play tieback of the future. The key assumptions were that plug and play is applicable to the UKCS. The design will follow an 80-20 rule. It would be too expensive to design a system suitable for 100% of the small pools. The system is designed with minimum protection for fishing interaction. To design our drill site, we broke the process down to two levels. The first level being the fundamental design philosophies, which help shape and guide our design, and the second is the functionality of the main components. So, our design philosophies. The map on the right shows the historical developments that we have reviewed to help develop our philosophies. And they were the Northern North Sea, Central North Sea, Southern North Sea, and the Murray Forth Basin. And these are indicated by the black dots, all of which are where small pools exist. In terms of well clustering, following a review of the historical data, you can see from the graph that the preferred layout is the manifold. Therefore, we have adopted this as our preferred design. We believe that this has the best balance of flexibility and future expansion. In terms of the developments being diver assist or diverless, the vast majority of UKCS developments are diver assist, and experience shows that diverless systems are more expensive to install. Therefore, we do not envisage diverless systems being used for small pools. However, we do think that there is room for some diverless equipment. The simpler operation of diverless equipment could have a substantial impact on installation and recovery times. So the philosophy is a diver assist design supplemented by diverless technology when it can be proven to be cost effective. This is the term Diver Plus. In terms of tree design, a common issue with tree design is the vendors will design their tree suitable for their own control system and are reluctant to change the design. Therefore, we propose to remove all bespoke equipment from the tree and use a standard design. Now, when we say standard design, we do not mean a standard design across the industry, but a vendor standard design. This will allow you to go to any vendor and pick the tree that is most suitable for your development. For flow management, we are proposing a standalone module for flow management, metering and sampling, and this will be provided in a standalone module rather than having on a manifold or a tree. For pressure and temperature, we follow the 80-20 rule. We do not want to design the system for HP or HT, as it would make the system massively over-designed for the majority of fields.
So,
Coming on to our modular components in turn, for jumpers connecting to the manifold or tree, we do not believe rigid spools are suitable for the reuse in the circular economy, as they are not flexible to varying drill site layouts. We think that solution is unbonded flexibles or the relatively new technology of composite pipes, which are particularly suited to reuse as they don't suffer from corrosion or age degradation, although flexibles do have a better track record. The first graph along the bottom shows the historical jumper lengths, with 80% falling between 25 and 60 metres. So to standardise for small pools, we are proposing to standardise a length of 60 metres. In terms of diameter, the second graph shows a production jumper is universally 6 inch, and the third graph shows that a gas lift is universally 2 to 2.5 inch. Therefore, we can standardise on jumper ID as well. Water injection is not seen as a normal requirement in general for the North Sea, especially in the case of small pools. However, should it be required, the system is such that it can be easily added. For jumper connections, there is a big opportunity to reduce installation and recovery time by removing flanged connections and replacing them with a single connection. This can be made by a diver or an ROV, and instead of doing 12 to 20 bolts, there is one single connection to be made. This could reduce connection and disconnection times from 12 hours down to 2 or 3. So we now look at the manifold. The manifold structure we have looked to simplify as much as possible to reduce costs and increased versatility across fields. There is no test loop, metering or chemical injection, simply production and gas headers and branches, and there is space for 2 SCMs, Subsea control modules. The manifold pipework will be protected by the same corrosion coating system used in the pipeline, and this will be covered in Crondal's presentation later on. The structure design does not need to be fission friendly, therefore it can be gravity based, making it easier to deploy and recover. This also fits with the philosophy of leaving a clean seabed. It can also be slab-sided, reducing footprint and cost. The final component of the plug-and-play drill site is the flow management package. This module will be located next to the tree and will provide any custom requirements normally found on a tree or manifold. The key point about this package is that all components are modular and replaceable. So for example, during field life, you could add a new chemical injection point or erosion monitoring should your production fluids change. Some developments which are simple may not require this package at all. So if we move on to installation and recovery, a crucial aspect of enabling reuse in a circular economy is the installation and recovery of equipment for redeployment at the next drill site. The main objective is we must guarantee the integrity of the equipment during installation and recovery when it is at its greatest risk to damage. Also, optimising offshore schedules by reducing activities and maximising vessel availability by reducing component size and weight. We will want to monitor installation and recovery, so at the end of each deployment we can ensure that the components are not damaged during installation or recovery. The use of gravity-based structures allows us for quick installation and recovery without the need for piles. Since we have a standard component, we can have standard installation methods which are best suited to ensuring reusability. For jumpers, we believe that there is a time saving by using the single connection method. The final solution is more of a development item where we think the jumper carousels could be developed to remain on the seabed for the field life, allowing the jumper to be reeled out at the beginning of field life and reeled back in at the end. The carousel is then recovered, which limits the loading on the product. This type of thing does exist, but is normally used for installation only. So that was the process that we went through to end up with a typical small pool drill centre shown on the right. The two main conclusions that we can take from the study are: there is an economic justification for plug-and-play drill site, particularly when you consider reduced installation and recovery times, and of course the reuse of equipment. The second is that the technology to achieve this is largely available and proven, with a little development required in areas such as installation techniques. Further work that could follow on from this study is a more detailed look at the ownership model and what it might look like for reusable equipment, taking into account the whole supply chain. As I mentioned before, we think that more work is required to develop installation and recovery techniques that guarantee the integrity of the components and allow them to be reused with confidence. So we now move on to the reusable control system. The reusable control system is a system where all components are designed for recovery and reuse. These components are designed to operate for 4 to 5 years before the recovery, refurbishment and reuse process begins. Today, current practice combines topsides and subsea equipment, where the topside equipment is permanently installed on a host facility and would normally remain there until the system is decommissioned. This does not easily lend itself to reuse. Deploying the equipment at the drill site gives greater access to the equipment, allowing easier recovery and relocation. There is the possibility that the umbilical from a conventional system could be reused, but for the purpose of this study, we have concentrated on deploying equipment at the local drill site. So if there's no umbilical in the system, there are some benefits. The umbilical is often seen as an expensive piece of equipment to purchase and install. It can be considered to be a long lead item. It is unlikely the umbilical is suited to being installed and recovered multiple times. There is also a considerable cost associated with replacing a faulty umbilical. Also, retrofitting a J-tube to a host facility to accommodate a new development adds considerable cost to the project. So, if there's no umbilical, we need to find other ways to provide the services normally found in the umbilical, such as power, communications, hydraulics, and chemicals. The block diagram here shows how each of these services are interconnected and which components they supply. Power and communications are required for the hydraulic power unit, the subsea control module, and the chemical injection unit. Hydraulics are fed from the hydraulic power unit via the subsea control module to the subsea tree, and chemicals are fed direct from the chemical injection unit to the tree. So we have reviewed different types of technology to see what is available to provide these services normally found in the umbilical. For power and communications, using ocean current to trickle charge batteries and acoustic comms, East Coast Oil and Gas's Power Hub is one example of how to power subsea components. Ocean Power Technologies Powerboy with inbuilt communications uses the ocean waves to generate power and trickle charge batteries that can provide power for components on the seabed. Similar to the Power Hub, Current to Current's sea socket also uses ocean current to generate power and trickle charge batteries to supply local components with power. Communications is provided by acoustics to the surface. If hydraulic power is required, hydraulic power can be supplied using a subsea hydraulic power unit, similar to the one provided by Siemens, which has the capability of providing 2 to 4 trees and could be controlled by the SCM. An alternative hydraulic power is the all-electric tree. If this was to be used, it would just require extra power modules to be added to the system. The new internal coating systems will reduce the quantity of chemicals required, and this has been looked at in the Crondall flow assurance study, which will come later. Should chemical injection be required, it can be provided by a subsea chemical injection unit, such as the HEI Technologies integrated pump and tank solution, which can bunker up to 15 cubes of chemical, which is considered to be sufficient along with these coating systems. A completely alternative system to put in the components on the seabed is the production control buoy, such as the one supplied by ProServe, which has the hydraulics, the chemicals and the power and communications located on the buoy. Tree services are supplied direct to the tree via a downline. Power to the buoy is provided by solar panels and could be supplemented by subsea power, such as the power hub or the sea socket. So, now that we have established the equipment to replace the services normally found in the umbilical, the following slides will show some architectural concept layouts of how the system might look. The first one shows a surface power and communications buoy providing services to subsea equipment with communications sent to the host facility via satellite. The second option shows power generation on the seabed to supply the subsea components, and communications is provided through acoustic communications to a buoy on the surface and then via satellite back to the host facility. Option 3 shows the production control buoy delivering the required services to the subsea tree via a downline. Communications in this case could be provided by a line of sight system as well as via satellite or 3 or 4G. And our final option also has power generation on the seabed along with other components. The communications in this case is transmitted wirelessly along the pipeline back to the host facility. This type of system could also be integrated with a pipeline integrity monitoring system, which will be covered by Crondall. So, in order for us to supplement the plug-and-play tieback of the future by incorporating a reusable control system, we need to compare all 4 options in order to carry one forward. It should be noted that all options are feasible and would meet the requirements of a reusable control system. The renewable power sources have the capacity to provide the necessary power for the control system. So each option was assessed against the 6 different criteria: system robustness, installability, reusability, maintenance access, the average TRL status, and the cost differential against the least expensive. Each criteria was given a value of importance between 1 and 3, with 3 signifying the most important. In this case, system robustness, reusability, and the cost differential. Each option was then scored on each criteria and given a score between 1 and 5, where 5 is very good and 1 was poor. As you can see from the matrix, the results show that the systems were very close in comparison, but option 2 was chosen to be applied to the tieback of the future. So the sketch we've got here shows what the tieback of the future might look like with a reusable control system incorporated into it. The subsea hydraulic power unit and the chemical injection pumps are grouped together in one structure to aid installation and recovery. We also created 2 GAs of the same layout. The one on the left-hand side shows the layout of the system, and the one on the right-hand side shows the system zoomed out to incorporate the fishing safety zones. In summary, we feel that the reusable control system is a feasible alternative to the umbilical. The equipment is better suited to reuse, and the development of the technology is in the later stages. Some further work that we feel should be carried out is on the security of the communications network and optimising the power required by the subsea equipment. And that's it.
Thanks, Gordon. Cheers.